I'm a chemical, material, and mechanical scientist, experienced particularly in additive manufacturing techniques for metals and their potential application in space manufacturing. In order to push for ambitious exploration goals and extending human economic reach beyond low Earth orbit, sustainable and affordable exploration of the moon and beyond is a necessity, which calls for production of consumables for autonomous or human activities from the raw material that is found on lunar surface or any other planetary bodies. This is an approach that is called In-Situ resource utilization, or in simpler words, living off the land. In-Situ resource utilization by now is focused only on the extraction of oxygen, mostly from the lunar regolith or other types of regolith. But what is important is that after the extraction of the oxygen, what remains is a mixture of metallic and metalloid elements. That this feedstock can be used, incorporated with additive manufacturing processes and technologies in order to produce functional parts or load-bearing parts that can be used in the potential infrastructure that is going to be built on these planetary bodies. The important point here is that the mission architecture for future lunar exploration is not defined yet by the space committees. So the important point that here we are trying to deep dive into is to understand the process itself. And we are using powder laser-based additive manufacturing techniques that using this AMISRU feedstock as the powder feedstock, and also a kind of processing with laser that you somehow consolidate the final piece. So the idea and the focus of this project would be to deep dive on the reliability, repeatability, and reproducibility of such process that if you can prove that, and if we can understand and learn from it, we can somehow use it in the future for any type of parts. And also we need to formulate a kind of a database that embodies a full characterization of this feedstock material and also the mechanical properties of the potential final consolidated parts. We also know that the metallic parts, the functional or load-bearing parts on lunar surface will undergo a completely different environmental effects, and also the gravity that they're under is somehow totally different than what same parts would experience on Earth. So this would call for a re-renderation of the standards for the parts that needs to be used on such infrastructures. The AMISRU project is funded bilaterally by European Space Agency ESA under the program OSIP and Swiss Space Center Mesure de Positionnement 2020 funding for a minimum of 2 years of study. The laboratories involved in EPFL are the Thermomechanical Metallurgy Laboratory LMTM and the Space Center EPFL. The metallic AMISRU byproduct that is going to be used as feedstock incorporated with the AM technologies that we are using is very heterogeneous in its chemical composition. And also it contains excessive amounts of low vapor pressure elements. So this combined unique characteristics of such feedstock, we believe that is going to result in high complexities in the process. Actually, complexities that we expect to be in levels that have not seen before. So we have considered appropriate measures in upgrading the already existing laser-based additive manufacturing technologies by addition of modules that would give us higher degrees of control and degrees of freedom for the process optimization and observation of the process.